We have Abdul Zalloum to talk about the sublinearly Morse boundary for the mapping class group via Cat0 cube complexes.
Yeah, okay, thank you for the introduction. And I can't really say thank you for inviting me because in some sense I invited myself, but thanks everyone for coming. Okay, so right, so this is this is joined with Matt Durham, and so what's the story? So the story is as follows. So we have two goals, and the first goal is to understand the geometry of sublinear Morseness in hierarchically hyperbolic spaces, and that's a category that includes the mapping class group, Teichmuller space, and all known co-compact Cat0 cube complexes. So the plan is we want to understand the geometry of sublinearly Morse geodesics and the sublinearly Morse boundary, and how it connects to the geometry of the curve graph. The mapping class group comes with a hyperbolic space that it acts on nicely, and we want to see how the sublinearly Morse boundary connects to that. Okay, so that's one of the goals. Now the other goal is in order to accomplish the first goal, in order to see how the sublinearly Morse boundary interacts with the curve graph, we're going to investigate and establish lots of connections between Cat0 cube complexes and hierarchical hyperbolic spaces. And in some sense, the tools we build, the connections we build between Cat0 cube complexes and hierarchical hyperbolic spaces are as interesting as the theorems we get about the sublinearly Morse boundary. So you can think of this as an independent, separate goal. So, so what we're going to do, we're going to see some correspondences between HHSs and Cat0 cube complexes, and statements about the sublinearly Morse boundary are going to follow for free. So that's the plan. Okay. Okay. So what's a Cat0 cube complex? So we know what a Cat0 space is, thanks to Kim from yesterday. A Cat0 cube complex is a Cat0 space which can be built by gluing Euclidean cubes isometrically along faces. Okay, that's what a Cat0 cube complex. So a picture of this kind is a Cat0 cube complex. Now, given a Cat0 cube complex, you can define what's called the hyperplane. And a hyperplane is a convex subspace of the Cat0 cube complex, which cuts it in half. It cuts it to two pieces, a right piece and a left piece. So that's what the hyperplane is. So for example, this red piece here is a hyperplane in this Cat0 cube complex. Okay. Now, if I hand you two disjoint hyperplanes, H1 and H2, so two disjoint hyperplanes, H1 and H2, are said to be L separated if every chain of hyperplanes meeting them both has cardinality at most L. So you should have a picture maybe like this in mind. So you have two hyperplanes, H1 and H2. And we're going to say that these two hyperplanes are L separated if the largest chain of hyperplanes that meet both has cardinality at most L. And I'm going to show you that this property here is a hyperbolic-like property. This property is going to quantify Morse, it's going to quantify sublinearly Morse, it's going to quantify. We're going to see lots of connections between this property and hyperbolicity. And in fact, a Cat0 cube complex is hyperbolic if and only if every pair of hyperplanes satisfy this property. So that's the idea. Okay, so let's quickly see an example to see how this actually relates to hyperbolicity. So let's move this somewhere else and maybe drag, trying to be fancy. I don't know if it's going to work or not, but so let's see. So I have the hyperbolic plane here, and I have these two red hyperplanes, which I'm highlighting. The one on the, so maybe here is the first red hyperplane, and here is the second red hyperplane. If you count the number of hyperplanes that intersect both, you're only going to come up with one, right? So how many hyperplanes intersect both? Well, there is this one here. So that's a hyperplane that intersects both, but that's it. There's nothing else that intersects both hyperplanes. So you can see that this separation is intimately connected to the contraction property and hyperbolicity. Okay. Now the following statement can be made precise due to Sagiv, but the idea is, if you're working with a Cat0 cube complex, then the language is the language of hyperplanes. Every notion that you care about in a Cat0 cube complex can be described entirely in terms of hyperplanes. All right, so and this is a really pretty theorem that due to a given, it can be made more precise, but it really essentially says this. It says, if you understand hyperplanes and the way they interact with one another, you understand exactly what the cube complex looks like. All right, so for instance, as I mentioned a second ago, a space X is hyperbolic if and only if every sufficiently far pair of hyperplanes, H1 and H2, are L separated. So this notion of L separation, it characterizes hyperbolicity. But the point is, you have a geometric notion, which is hyperbolicity, that you care about. And in the class of K0 cube complex, this geometric notion is described purely in terms of hyperplanes. But this is not special to hyperbolicity. Anything is, what I'm saying is that anything can be described in terms. For example, let's say, you're in a K0 cube complex. You would like to understand if an edge path is a geodesic or not. And it turns out that an edge path is a geodesic if and only if it never backtracks along the hyperplane, if and only if it never crosses a hyperplane and it crosses it again. So you have two notions, hyperbolicity and geodesics, and both of these notions are described purely in terms of hyperplane. And the list goes on and on. I mean, you can describe distance in terms of hyperplanes. Distance between 2 points is the number of hyperplanes that separate them. But that's the idea. All right. Okay. Any questions so far? So please, if you have a question, unmute yourself and ask, because I may not be able to see the chat, although I'm trying to. But okay, so a space is said to be.
Sorry, Abdul, I still have a question. I probably skipped the first maybe minute of the talk. So you introduced the notion of L separability, yeah? And you had the hyperbolic example. So first of all, it's cat -1, so definitely cat 0. And but you wrote this, you drew like the one line. I mean, you could draw any geodesic and it would still intersect the two hyperplanes.
Yeah, so the point is, give me any other hyperplane. So they're called L separated if the number of hyperplanes that meet them goes to at most L, not the number of geodesics. Of course, there are infinitely many geodesics that meet.
Sorry, correct. But again, in hyperplane.
Yeah,
again,
so here is, give me any other hyperplane. So here is a hyperplane. Yeah. And you see it's going to continue.
Oh, this is important. Oh, this is what I wanted.
Yeah,
I see.
Okay,
this is
okay, yeah,
example.
that's okay.
Sorry,
No, that's a good question. Okay, right. Okay.
Thank you very much.
Yeah. Now, at essence, a space is said to be hierarchically hyperbolic. So a space, an HHS, is abbreviating what's a hierarchically hyperbolic space is. So a hierarchically hyperbolic space, in essence, it's a geodesic metric space X, which comes with a family of projection maps to delta hyperbolic spaces. All right. So here I have a family of projections to a collection of hyperbolic spaces, and this is the index set indexing the hyperbolic spaces. And the idea of an HHS is that this family of projections to hyperbolic spaces, they control the entire geometry of the HHS. In the exact same way hyperplanes control the entire geometry of a K0 cube complex. Okay, so it's the main philosophy is the same. The main tool in K0 cube complex is that of hyperplanes, and the main tool of hierarchically hyperbolic spaces is the collection of hyperbolic spaces and these projection maps. And you can understand anything, any geometric notion that you want about an HHS using such maps. And this is due to Berstock, Hagen, and Sisto, and it's also due to Bowditch in slightly different setting, but they both have the same idea. It's category of hyperbolic spaces and maps to them. Right. So I want to mention one thing. This is the index set that index the hyperbolic spaces that you have, and this set comes with a partial order. It's called nesting. All right. And this partial order contains a unique maximal element that we're going to denote S. Right. So you have a partial order and a unique maximal element denoted S. Right. Every single element in the collection nests in this unique maximal element. The hyperbolic space associated to this unique maximal element is denoted CS. Okay, and it's called, we're going to refer to it as the top level curve graph. So if you're familiar with the mapping class group, that's exactly the curve graph of the mapping class group. If you're familiar with right angled arcing groups, that's the contact graph of the Salvetti complex. Right, so that's the idea. Okay, so I'm claiming that every single geometric notion of interest in an HHS can be described via these maps and via these hyperbolic spaces and the maps to them. So let's see a couple of examples. So an HHS is hyperbolic. So you would like to understand whether an HHS is hyperbolic or not. And here's a pure description of where HHS is hyperbolic purely in terms of such maps. An HHS is hyperbolic if and only if it's quasi-isometric to the top level curve graph. So if and only if the map, so you have a collection of maps here that go to the collection of hyperbolic spaces, all right? And HHS is hyperbolic if and only if the pi sub S map is actually a quasi-isometry. Okay, so here is a characterization of hyperbolicity in terms of such maps and such hyperbolic spaces. Another thing that you can characterize purely in terms of projections to these hyperbolic spaces is the notion of median paths. So I'm not going to tell you what a median path is. So you can take this as a definition if you want, but a median path is something that's defined independently. It's defined aside from this property. And it turns out that a path is median, all right? So a path is median if and only if the projection of this map to every hyperbolic space, so you project, I hand you a path gamma, and this path is median, if and only if its projection to every hyperbolic space does not backtrack, right? It could backtrack by a uniform amount, but it's okay. So you could backtrack by a distance 5, where 5 depends only on the HHS, right? But that's the idea. Okay. So if you know HHSs, those are also called hierarchy paths. But the point is, right. So median paths can be defined independently of this property, right? So if you know median, that's just a path where the median of 3 points A, B, and C is exactly B. It's the point in the middle, and such paths are described purely in terms of the projections to hyperbolic spaces. So again, if you don't know what median paths is, from now on, just take this as a definition. A path is median if and only if its projection to every hyperbolic space is an unparameterized quasi-geodesic. Okay, so we see that there is some similarity between CAD0 cube complexes and hierarchically hyperbolic spaces, and the similarity is summarized in this slide, perhaps. So hyperplanes control the entire geometry of a CAD0 cube complex. In a similar fashion, such projections to hyperbolic spaces control the entire geometry of an HHS, right? And here are two examples which look quite similar, right? Where you have a notion, a purely geometric notion, which is described purely in terms of the hyperplanes in the cube complex case, and the projections to hyperbolic spaces in the HHS case. Okay, so what do we care about in this conference? We care about going to infinity. One of the things we care about is the sublinearly Morse boundary and the sublinearly Morse geodesics. So a natural question to ask is, how are sublinearly Morse geodesics characterized in CAD0 cube complexes? The claim is that they can be characterized via hyperplanes. So let's see that, right? So this is a theorem due to myself, Devin Murray, and Yulan Cheng. And so it says the following. It says a geodesic ray is kappa Morse if and only if it crosses an infinite sequence of hyperplanes. So you have an infinite sequence of hyperplanes where the crossing points grow sublinearly. It grows like kappa, and how separated two hyperplanes are also grows like kappa. Okay? So let's think about this for a second and try to parse it. Being kappa Morse just means you cross an infinite sequence of special hyperplanes, and you cross them at a sublinear rate, so this distance grows like kappa. And the number of hyperplanes that's allowed to meet two consecutive ones also grows like kappa. All right, so that's right. So that's the idea. Okay, now so that's the story in CAD0 cube complexes, and so now let's see what's the story in hierarchically hyperbolic spaces. So the claim that's written here is that in hierarchical hyperbolic spaces should be able to characterize everything in terms of projections to hyperbolic spaces. So a natural question to ask is, how do sublinearly Morse geodesics, how are they characterized in terms of projections to hyperbolic spaces? And this theorem, so this theorem here gives you an answer to that. So let's see. For a kappa Morse, so suppose you have a kappa Morse quasi-geodesic ray Q. There is a special, so you have a quasi-geodesic ray Q that defines a point in the kappa boundary. And a point in the kappa boundary is an equivalence class, right? Now there's a special representative of this element in the boundary called H, okay? There's a special representative H that we call a median ray, right? So that's the first part of the statement. You hand me a random quasi-geodesic, which is kappa Morse. I can replace it by a quasi-geodesic ray, which is a median ray. I didn't tell you what a median ray is, but I gave you something that characterizes it. So that's what the so a median ray is just something that projects to an unparameterized quasi-geodesic in each hyperbolic space. Now, for a median ray H, we have the following. The first statement says that if you know that this H is kappa Morse, then the projection to each hyperbolic space has to be coarsely bounded above by kappa for every non-maximal domain. So let's think about this for a second. The collection, the index set comes with a partial order, and there is a unique maximal element, right? This statement here says, if you know that H is kappa Morse, then the distance between the projection of H of 0 and H of t is going to be bounded above by kappa of t in every domain U except for the top level one. Right? So that's what the statement is saying. And the converse of this statement is true, modulo a small thing. So if I hand you a median ray H that satisfies this property, so suppose H is a median ray where the distance between H of 0 and H of t is at most kappa of t, and this is a course at most, up to a multiplicative error, just an additive and a multiplicative error. So if the distance in each hyperbolic space is at most kappa of t for every non-maximal domain, then H has to be kappa to the p Morse, where p is a power that only depends on x. So it doesn't change as you change kappa. So I should remark that this part here, it also assumes that kappa is a function where kappa to the p is again sublinear. Otherwise, this wouldn't make sense. So it's something like a log function. If you take a log and you raise it to any power, you remain sublinear. But if you take a square root and you raise it to power 2, then it's not a sublinear function anymore. Do we have any question so far?
I'm sorry, Abdul, can you explain what S is again?
Right. So let's see what S is. So let's go back to the definition of hierarchical hyperbolicity. So the HHS by definition was a space that came with a collection of hyperbolic spaces, right? So it's a space that came with a collection of hyperbolic spaces and projection maps to them. Okay, yeah. And I mentioned that this index set comes with a partial order, and there is a unique maximal element called S. So S is the unique maximal element, and CS is the hyperbolic space indexed by that S. Okay.
Yep, got it. Thank you.
Okay, so that's like the curve graph if you know the mapping class. That's really the idea, or the context graph, or okay. Okay, so any other question? Okay, so we have these two categories of, so we have Kaiser cube complexes on one hand, where everything is supposed to be described via hyperplanes, and we have the description of kappa Morse quasi-geodesics or geodesics in terms of hyperplanes. And we have HHSs, where you have this family of projections to hyperbolic spaces that are supposed to describe everything. And here they do. You can characterize kappa Morseness entirely in terms of their projections to hyperbolic spaces. Now, the most interesting part to me about one of the most interesting parts to me about this theorem that I'm going to show you in a second is that in order to prove this theorem here, we're going to actually use this theorem. So this theorem here is going to be a reflection, this characterization, which has nothing to do with cat-zero cube complex. I mean, this statement here has nothing to do with cat-zero cube complexes. You only see hyperbolicity and projection maps. Right? You don't see hyperplanes or anything. However, the proof is going to be a reflection of of this statement. So we're going to use this statement in the proof. So let's see. And my plan for the rest of the talk is to show you some parts of such connections, some parts of how do HHSs and K0 cube complexes relate. Okay, any question? So I'm going to show you a sketch of the proof. All right, so let's see. So start with any median ray H in an HHS, okay? And start with any 2 points X and Y in X. One thing we prove in collaboration with MathTerm, so this is a statement that, again, it's independent of the kappa boundary. So this, okay, so what's the statement here? For any median ray H and for any 2 points X and Y in X, there exists a K0 cube complex, Q, and a nice quasi-isometry between Y and Q, where Y is a subset that contains both H, X, and Y. So let's again think about this for a second. I start with any random median ray and any points X and Y, and can find a subset Y in X that contains both H, X, Y, contains both H and X, Y. Okay, and this subset, we show that there is a quasi-isometry between this subset of the HHS and some K0 cube complex. And the constants of the quasi-isometry are uniform, they depend on nothing. Okay, so maybe here is a picture just to see what's going on. I start with a random H, not necessarily kappa Morse, there is no assumptions, it's just a median ray. I have a median ray H, and I have 2 points X and Y. I can find a subset Y of my space X. Okay, so here is the subset Y. It's this green, it's this green piece. It's a subset that contains H, X, Y, right? So I can find a subset Y, and I can find a nice quasi-isometry. It's a quasi-isometry with an extra property. So I get K0 cube complex Q. Right. So that's the first step of the proof. All right. Now, the second step, again, doesn't involve kappa Morseness at all. The second step, or lemma or theorem says that if you have a median ray H, whose projection to the top level curve graph is infinite, so you start with a median ray, whose projection to the top level curve graph is infinite, then G of H, this G of H here, the copy in the cube complex has to cross an infinite sequence of L separated hyperplanes at the same speed H travels in CS. This is going to take a few minutes to actually parse what's going on. So let's think about it. So I start with a median ray H in my HHS, and I have 2 points X and Y, and I find a subset Y, right, which is quasi-isometric to some K0 cube complex. So I have copies of X in the K0 cube complex, a copy of Y in the K0 cube complex, and a copy of H in the K0 cube complex. The assumption of part 2 is that this median ray here is not just any median ray, it's one that projects to an infinite diameter set in the curve graph. So I have the projection of H in the curve graph has infinite diameter. What the statement is saying, it's saying the following. It's saying that if you have 2 points here, H of S perhaps and H of T, and you look at the projection in the top level curve graph, you look at the projection of H of S and the projection of H of T. So here are the corresponding projections. If the distance between these projections here is N, and you go and you look at what's happening in the approximating cube complex. So if you look at what's happening in the approximating cube complex, you're going to see that. So here is the approximating cube complex, and here is the quasi-isometry G. In the approximating cube complex, the corresponding red points are going to be separated by a collection of L separated hyperplanes, and what's the cardinality of this collection? It's coarsely N. Okay. So to me, this is an interesting statement. Why? Because it says that, well, what does it mean to move in a hyperbolic-like direction in HHS? Moving in a hyperbolic-like direction in HHS means that you're moving in the top-level curve graph. Moving in a hyperbolic-like direction in a K0 cube complex, it means that you're crossing some of these L-separated hyperplanes. And this theorem here says that these two things coincide. If you make distance in the K0 cube complex, sorry, if you make distance in the curve graph, then you have an approximating cube complex where you're crossing lots of L-separated hyperplanes. And the L is uniform. The L also only depends on S. All right. So these two statements are, again, so far nothing to do with the kappa boundary. All right. And now let's go back to what we were trying to do. So again, what was the statement we started proving? The statement we started proving was this. So so I wanted to prove this statement, right? That if I'm kappa Morse, then the distance in each hyperbolic space is bound above by kappa. And if the distance in each hyperbolic space is bound above by kappa, then H has to be kappa to the P Morse. Now, this direction is immediate, so I'm not going to talk about it. This direction is 2 lines. If you want, you can ask me about it after the lecture. But what I want to discuss is the more interesting direction, which is this one. I have a median ray that I know nothing about, except for its projection to each hyperbolic space, aside from the top level, is bound above by kappa. Okay? And from that, I'm going to deduce that it has to be kappa to the P Morse. So let's see how we do that. All right? So let's, so here it is, okay. So I have a median ray H, and it satisfies that property. The distance in each hyperbolic space is bound above by kappa. Right? Now, what the condition here is saying, it's saying that the distance in each hyperbolic space is small. Right? You have a bound on the distance in each hyperbolic space. Okay? Now the distance formula, because the distance in each hyperbolic space is small, all right? The distance between H of 0 and H of t, it has to be witnessed somewhere. Okay, so this is by the distance formula. So the distance, you know, it's small in each hyperbolic space, so it has to be large somewhere. So one thing that you can show is that if you have this condition, if it's smaller than kappa in each hyperbolic space, then the distance in the top level curve graph has to be at least t over kappa to the p of t. And there is an argument to be made here, but the idea is just the distance formula, right? If you have the distance between H of 0 and H of t is the sum of distances in each hyperbolic space. And we know that the distance in each hyperbolic space is small, right? So it has to be large in the top level guy because it's the only one where it's not small. So the distance in the top level curve graph is going to be at least t over kappa to the p of t. Now you can wiggle this a bit and show that, in fact, the distance in the top level curve graph is going to be larger than t minus s over kappa to the p of t for any s and t in 0 infinity where s is less than t. So if you give me, so maybe here is a picture that describes what's happening. So the assumption was that the distance in each hyperbolic space was small. In each u, it was at Morse kappa. You can use that to show that the distance between the corresponding points in the top level curve graph has to be at least s minus t, right? It has to be at least s minus t over kappa to the p of t, right? Now here is my 2 points in the actual space in the HHS. Now, items 1 and 2 of this proof, they showed you that if the distance you make here is like n, you must cross at least n separated hyperplanes in the cube complex. So if you go look at the cube complex here, you're going to cross at least, right? So you're going to cross at least t minus s over kappa to the p of t separated hyperplanes. And then the characterization that I mentioned, the characterization of kappa Morseness in Cat0 cube complexes is going to imply that this guy here is kappa to the p Morse, right? Because recall, in a Cat0 cube complex, a geodesic is kappa to the kappa Morse or kappa to the p Morse, if and only if it crosses infinitely many ill-separated hyperplanes at some kappa rate. And that's exactly what we have just shown. We have shown that you do cross infinitely many ill-separated hyperplanes at some kappa rates. Okay. And then that's, and then that implies that this piece here is also going to be kappa Morse. Now, the thing I did not explain is why did we even pick 2 points x and y to begin with? Why not have just done the argument with h? And the reason is, knowing that this h here is kappa Morse in the subset y says nothing about whether it's kappa Morse in the ambient space or not. because this is something that came up in Castro's talk yesterday. You could have a quasi-symmetric embedding of H2 and H2 times R. And H2, everything is Morse, but in H2 times R, nothing is Morse. But the trick is you just pick 2 points, X and Y, and you just carry them along the entire time. So here, we deduce that this guy is going to be kappa Morse. And in cat zero cube complexes, kappa Morse is equivalent to kappa contracting. Then you show that because this guy now is kappa contracting, the projection of Gx and Gy here has to be small. And then you show that the projection of X and Y here has to also be small. That's the idea of it. All right. Any question? Please ask me. Questions?
Sorry, what about the distance formula?
What about the distance formula?
Distance formula for the Hieracy space.
What about it?
Yeah, what is the distance formula?
You want the statement of the distance formula?
Yeah.
Yeah, okay, so the statement, it says that, so let me put it in where it belongs. So the place where it belongs is here. So this slide was saying that everything in HHSs can be described by the family of hyperbolic spaces that come with them. And one particular manifestation of that is the distance formula, which says that the distance between any points X and Y is coarsely the sum of their projections to It's coarsely the sum of their projections to the collection of hyperbolic spaces that you have, where this sum is taken over. So it's taken over, it's not taken over every single U in I. It's taken over U in I, where the distance between X and Y in U is large. So if the distance between X and Y in some of the U's is small, you just ignore that U. Okay, but the idea is the distance between X and Y is just the sum of the projection of X and Y in each hyperbolic space. Does that answer your question?
Yes.
Okay, and one of the essential parts of this proof was that we knew that the distance was small in each proper domain, and that let us deduce that the distance had to be large in the top level guy. And then we used this statement again, and to me, I really like the statement, so I'm going to keep coming back to it. So the statement here, it says that if you have any median ray in HHS that makes distance n in the top level curve graph, then there's an approximating cube complex with uniform quality business, uniform quality quasi geodesics, such that in the approximating cube complex you cross as many hyperplanes as the distance you have made in the top level curve graph. And again, this really shows that hyperbolicity, the way hyperbolicity is manifested in HHSs and Kaiser cube complexes coincides. That's one nice aspect of the statement. All right, so good. Now, what else do we know about the kappa boundary? So this is again, everything here is joined with that term. So take X to be an HHS, all right? And suppose, don't ask me what this is, it doesn't matter. So to have an HHS with some condition, so it still includes all the examples that you can think of, right? Okay, and suppose you have pi sub S. So suppose this is the projection map that goes from X to the top level curve graph. Right, so this is the special projection map that goes to the top level curve graph. And suppose you have a kappa, you have a sublinear function kappa, where kappa to the p is also sublinear, where p is a number that depends only on X. So it's like, it's like the complexity of, it's like, it depends on the genus of a surface if you want. Okay, so I have a function kappa, where kappa to p is again sublinear. So we prove that this map here that goes from X to the curve graph, it induces a continuous injection between the kappa boundary with respect to the topology Castra described earlier. So you get a continuous injection between this set, between this topological space and the Gromov boundary of the curve graph. So now, from now on, you can really think about the kappa boundary as a subspace. Well, it's a continuous injection. The inverse map may not be continuous, but you can think of it as a subspace of the curve graph. It sits in the curve graph, and in fact, it's sort of a generic in the curve graph, right? It's anyway. So okay. So now, actually, questions. Please ask me questions, and or don't. It's fine. If you have questions, just ask. No questions.
And
All right.
what is this P, capital P of this P?
What is the P? Yeah. Did you ask what's the P?
Yeah. What does P depend on?
P depends on nothing. That's what I'm saying. So P is just, it just depends on X. So it comes with the X data. So it doesn't depend on kappa. So it's a constant that determined by X. Okay. Other questions? Okay. So let me now give you some ideas of what's this business about cat-zero cube complexes and hierarchical hyperbolicity? How do they relate? Why do they relate? So let's think about it for a second. So first, suppose you have a finite set of suppose you have a finite set of a hyperbolic space. So F is a finite set of hyperbolic space, of a delta hyperbolic space. You can define the convex hull of Y to simply be the set F itself union the geodesics that begin and end on F. So you start with a set which is not convex and you force it to be convex. I mean, this is it's a very standard thing to do, right? You have something which is not convex, you add geodesics to make it convex. Sometimes you add geodesics to make it convex and it's not convex. So you do this again, and you do it again. But in hyperbolic spaces, you only have to do this one step. More generally, in a cat-zero cube complex, you might have to do this 5 steps, or 5 only depends on the cat-zero cube complex. But it's a natural, that's how you convexify a given set. Okay. Now suppose that you have a set F in an HHS. You can define the hull of F. So I have an HHS. The hull of F is defined to be all points in the HHS whose projection to each hyperbolic space is within delta, and delta is the hyperbolicity constant of the hyperbolic space. So it's all points X and X whose projection to the corresponding hyperbolic space is within delta of the hull of the projection of F in the hyperbolic space. So maybe a picture would be helpful here. There is a much simpler description for this, by the way, via medians due to Brian Bowditch, which I like a little bit more, but this description here is more consistent with my talk, so I'm going to go with it. So so the idea is you have a set F. Okay, so you have a set F. So you have a map to each hyperbolic space. So you project F in each hyperbolic space. So you get this set. Okay. Now this is a set in a hyperbolic space. Maybe I'll call it F prime. So F prime is a subset. Horrible handwriting. Okay, so maybe so F prime here, which is the projection of this F in the hyperbolic space. That's a set in a hyperbolic space. You can take its convex hull. So you look at the convex hull of this. All right. So you add geodesics here. All right. So this new set now is the hull of F prime. Right. And the hull of a finite set in an HHS is defined to be all points. So it's all points X that live. So it's all points X in X, where if you look at the projection of X to the hyperbolic space, the projection of X is going to be within delta of this hull. That's the idea. All right. So again, the idea is just that you just do the hull in each hyperbolic space and you pull back. Okay, and so the following theorem is due to Berstock, Hagen, and Sisto, but it's also due to Brian Bowditch, and again a slightly different setting. So this is due to also Brian Bowditch and slightly well basically really the same essentially the same thing. So well, not really. There is some difference. So the statement here says, well, if you had me any finite set if you have any finite set F of an HHS, there exists a ket zero cube complex Q and a median quasi-isometry between Q and the hull of F, where the constants of this median quasi-isometry only depend on the cardinality of the set F you started with. So you started with a finite set F, and the statement says that you can approximate the hull of this finite set F by a ket zero cube complex where the quality of the approximation only depends on the cardinality of the set F you started with. Now, this approximation is not just a quasi-isometry, it's a particularly type of quasi-isometry. It's a median quasi-isometry, and this says that centers go to centers, and it really gives you lots. I mean, median quasi-isometries are extremely useful. I didn't realize that until I started working on this project. I'd love to tell you more about it, maybe at some point. But yeah, so you have a really nice quasi-isometry that goes from a ket zero cube complex to the hull of F. Any question about the statement of Burstock, Higgins, Sisto, and Bowditch in a slightly different setting? Okay, well, now this statement here is about finite sets, and this is a weak at infinity, and finite sets are just that we don't see them, we don't care about them, we don't see them, right? So so with Durham, we improved this statement, and we let it include median paths. Okay, so we show that for any collection F of for a finite set of points, and median paths H1 up to Hn, they don't all have to begin at the same point. They can begin anywhere they want. So you have a finite collection of points and a finite collection of median paths. Okay. Then the same conclusion holds. There exists a ket zero cube complex that approximates. You have a ket zero cube complex Q and a quasi-isometry between Q and the hull of F. And the constants of the quasi-isometry, they only depend on how many elements are in this set. I mean, this set is a priori infinite, right? Because you have these median rays, which are infinite. But the constants that you get here, they only depend on how many elements that you have in this set, which is an improvement of Burstock-Higgins system. But our proof, we just use their proof and we do some limiting argument. That's the best idea. So it's not. Okay. Any questions so far? Okay, so now
yeah. What about the median here of the HHS?
This statement, it holds for HHSs. Yeah. In fact, well, I don't want to get sidetracked now, but there is, in some sense, I can tell you more if you would like. It holds in coarse median spaces with a very mild. Basically, hand me a coarse median space that has this condition. Hand me a coarse median space where hulls of, so you can define hulls independently of the hierarchical hyperbolicity. So hand me a coarse median
here,
space.
I mean, what is the center? How to take the center of the HHS in HHS?
Can you ask again?
How to take the center of 3 point in HHS? You mean the projection to the hyperbolic space?
Yeah, exactly. You do it in each hyperbolic space and you pull it back. Yeah.
Okay, thank you.
Yeah.
I see.
Okay. Right. Now, an immediate corollary of this theorem is that there are a million definitions of kappa Morses. There is kappa Morse, kappa weakly Morse. Castro talked about some of them. Ruth Charney mentioned one of the definitions in her talk, which we're going to reference as kappa weakly Morse. And as an immediate consequence of this theorem is that all such statements are all the kappa Morse notions, whether it's kappa contracting, kappa Morse, kappa weakly Morse, whatever, they're all equivalent in a hierarchically. They're all equivalent in a hierarchical hyperbolic space, and the reason is you just hit the statement by this theorem. You take a median ray. You take a median. So first you show it for a median ray. So you show that for a median ray H, all the statements are equivalent. And the reason they're all equivalent is because they're all equivalent in a ket zero cube complex. That's known due to Chingrove, Raffi, and Tioza. So they're all equivalent to a ket zero cube complex, and you have a median quasi-isometry. a quasi-symmetry is not enough to get you this result, although it sounds like it. But you really need a median quasi-symmetry, because if you think about it, median quasi-symmetries, they say that centers go to centers. So it says that projections go to projections. One of the things Kessler mentioned yesterday is that one of the bad things about quasi-symmetries is that projections don't need to go to projections under a quasi-symmetry. However, under a median quasi-symmetry, there is a natural notion of projection, which is basically taking a center of 3 points, and that projection goes to the other projection. And this is one of the powerful things about having a median quasi-symmetry. The number of things that are preserved under median quasi-symmetry. I mean, if you take two hyperbolic spaces, x and y, and you take a quasi-symmetry between them, then it's automatically median. Every quasi-symmetry between two hyperbolic spaces is a median quasi-symmetry. So lots of properties that are preserved for quasi-symmetries between hyperbolic spaces, they're only preserved because the quasi-symmetry is actually a median quasi-symmetry. So if you give me any random spaces x and y, and instead of taking a quasi-symmetry, take a median quasi-symmetry, then lots of things that wouldn't be preserved would be preserved, right? So it's a natural thing. It's a natural thing to consider. For example, one of the things that are not preserved under quasi-symmetry is the notion of convexity or quasi-convexity. If you give me two Cat-zero cube complexes and you give me even an isometry, you can have an isometry. You have an isometry between two Cat-zero cube complexes where a convex set does not go to a convex set. Okay. However, right. So in general, yeah. So if you have two Cat-zero cube complexes and you have a quasi-symmetry between them, convex sets don't have to go to convex sets. But if you have a median quasi-symmetry between them, then convex sets will have to go to convex sets. So this business of preserving the convexity, if you have two hyperbolic spaces and one convex set in the first hyperbolic space, its image under a quasi-symmetry is going to be convex. But what I'm saying is that this property holds only because the quasi-symmetry between the two hyperbolic spaces is automatically median. So if you require an isometry between two Cat-zero cube complexes to be median, then that the quasi-convexity will be preserved. So lots of properties are hidden. Lots of hyperbolic, lots of things that seem to hold for hyperbolic spaces, they only hold because the isometry you have between hyperbolic spaces is a median quasi-symmetry. And this is, I think, you can milk lots of things out of this perspective. And yeah. Anyway, so okay. So maybe I thought I'll give you an idea of how we prove this theorem here. So again, this theorem was that if you have an HHS with some assumptions, then you get a continuous injection between the kappa Morse boundary and the Gromov boundary of the curved graph. So let's see what are the ideas that come into play with this. And again, we're going to use Cat-zero cube complexes. I mean, more, like Cat-zero cube complexes here don't appear in the statement, but they do appear in the proof, and that's true for almost every statement in our work. All right. So let's see how one would prove that. So I want to define a map between the kappa boundary and the Gromov boundary, right? So first, start with a kappa Morse quasi-geodesic ray Q, and let H be a median ray that represents it. And that's something that you can do. I mentioned that in one of the theorems. You can always take a kappa Morse quasi-geodesic ray, and you replace it by a particularly nice representative, and you essentially just do Arcella Ascoli, something like that. Okay. Okay, so I have now a median ray H that represents my my Q. Now there's a theorem due to Durham, Hagen, and Sisto where they prove that for any median ray, hand me any median ray in an HHS, there exists precisely one hyperbolic space where H has an infinite projection to it. Okay, there exists some domain, some hyperbolic space where H projects to an infinite diameter set. Okay. Now there is a theorem due to Rafi in the Teichmuller case, and due to Durham in the mapping class group case, that tells you if you have a median path that spends time n in a in a certain domain, then it has to stay for n time in a certain product in your space, right? If you have some median path that spends at least time n in some domain, then it has to spend at least time n in a certain product. All right. Now, as an immediate consequence of this active interval theorem, this U where H has an unbounded projection 2 has to be S, because otherwise H, the tail of H, is going to be contained in a product, and that can't happen for a kappa Morse guide, right? So the active interval implies that. So now we got ourselves a map. So we got ourselves a map from the kappa boundary to the top level curve graph. Now we want to show that this map is injective and this map is continuous. Continuity of this map is not interesting at all. It just works because the topology is defined in the appropriate way, right? Like, continuity of the map is not interesting. So I'm not gonna tell you about it. I'm gonna tell you about injectivity. So hand me two median rays, H1 and H2, which are not in the same equivalence class. Okay. And let's look at the approximating cube complex. So you have your median ray here. You have your two median rays, and you have a copy for those in a K0 cube complex. And F is a quasi-symmetry going this way. G is its course inverse. And recall, this is not just a quasi-symmetry; it's one that preserves median. This is going to be essential for us here. Now, I proved with Merlin a couple of years ago. We were studying sublinear Morseness in K0 cube complexes, and we proved that if you have two quasi-geodesics in a K0 cube complex, which are kappa Morse, and they do not kappa fellow travel each other, so you have two kappa Morse guys which are not in the same class, and you take the median of Q1 of t, Q2 of t, then that median has to be in a bounded set. So you take the median of Q1 t, Q2 of t, and you let t go to infinity. Even if you let t go to infinity, the median has to remain within a bounded distance from the origin, right? Just a compact, just a bounded set from the origin, all right? So this is a reflection of the thing Castro said, right? Like you have two quasi-geodesics, at some point they diverge. So there is a center, right? And that center is the median. Okay, so here's a picture, right? So we have this, right? So we have this. You're sliding to infinity, and you take the medians, and all the medians are going to be here. Because these maps are median preserving, right? The median on this side also has to be stuck here. It's a quasi-symmetry that preserves median. So distance between this point to this point is preserved, and the median goes to median. Again, this is an essential part of the statement here that the map is median. Okay, so this tells me that H1 and H2 are median paths where their median is within a bounded distance from the origin, but the map to so that's what we have now. But the map to the hyperbolic space is median preserving. So this pi sub s map, something I did not mention. I mean, just by the construction of the median in the HHS, it has to go to the median in the top level curve graph. That's how medians are constructed. You just take medians in each hyperbolic space and you pull back. And because median here is within a finite distance from the origin, the median here has to also be within finite distance from the origin, right? So this shows you that these 2 points have to actually be different. And thank you. I will stop here. Yeah. Please ask me questions if you have any.
Let's thank the speaker first.